And actually, probably it's a good opportunity to thank on behalf of all the speakers, in fact, all the participants, the organizers for such a nice meeting. Thank you. Okay, so I'm going to talk about a specific topic. So basically, I'm going to discuss something around stability, quantifies free stability in GVFs. I'll continue something that Udi alluded to in his talk, and okay, this is going to be a technical result that we managed to prove after some time, and it's actually quite surprising because I would have expected this to be known since the 1850s or something, and I'm still waiting for somebody to tell me, no, this is an old result, but still hasn't happened. Okay, so let me first start with just a few quick reminders. No, whatever. Okay, let me start first with a few quick reminders. So what's a GVF? You have a field, K, and then you have a measure space, let's call it omega of K, and you index, this omega indexes valuations of K, and you have the sum formula. For all x, okay, non-zero, the integral of the valuation of x d mu over all of omega is always going to be 0. Okay, so now what happens when you have a GVF extensions? So, okay, I mean, there are some degrees of freedom in the way you do this presentation, but if you have such a presentation for K and you have a GVF extension, then you can have a compatible presentation for L, so that would mean that you have omega of L. Okay, so here I would have maybe evaluation of L, and of course it restricts to evaluation of K. Actually, you can have several valuations that restrict to the same valuation of K, and this is going to, and the measure here is going to be the image measure of the measure here. So image measure. Everything is fine except one thing, that, well, all the valuations I consider here are non-zero. I mean, the trivial valuation is not very interesting, but of course there can be, there can be valuations here that restrict to the trivial valuation on L. So there's going to be a bunch of valuations here that all restrict to the 0 valuation on K, and this allows us to control here. I mean, you can think about this as being some kind of a measure 1 fiber over this point. Here you don't have no such kind of control. Okay, so let's do how one way to prove stability for codified free formula, for example, is say, okay, let's prove the uniqueness of heirs or co-heirs. So let's assume that I have L independent from M over K. What do I mean by independent? So L and M are two extensions. And what do I mean by independent? Let's say co-heir independent. So that means that K is going to be assumed to be existentially closed. L and M, I don't care. And then I can maybe take M extends K. I can take an ultra power of that. Okay, so this is M to the U, and this is K to the U. And L being finitely satisfied, the type of L over M being finitely satisfied in K, you don't need to know the logic in order to just say, okay, this just means that I can embed L here. Okay, so you can skip a lot of questions about the formal definition of the logic if you just accept the notion, the obvious notion of ultra power or ultra product in GVFs. And Udi kind of defined it. So let's just accept that it existed. It's relatively easy to give. Okay, so how am I want to describe the ambient field LM. So, okay, so first of all, just by general nonsense, K has to be algebraically closed because it's existentially closed. And this has to be a free, in the pure field setting, this has to be a free amalgam. So it's going to be the fraction field of L tensor M over K. But, okay, but now what about the space evaluation and the measure? Okay, so let's try to think about evaluation on LM. Okay, so let's say I have a little omega here. Okay, so I have a V. Okay, it's kind of cheating. I don't know if the index of the valuations are actually the valuations, but let's take evaluation here. So how can it look like? Udi already described. Let me go briefly again over the possibilities. Well, first possibility is that V is non-trivial on K. In that case, well, there is an entire fiber of possible extensions. Sorry, let me say slightly differently. Well, then you can show by general nonsense about stability in the continuous logic version of a valued field in which the real, the group of valuation being the reals, the group gamma is just the real, is completely fixed. So it's actually stable, and then you see that V has to be, in some sense, the free amalgam of its restrictions to L and to M. And then, over the restriction to K, there is exactly a fiber of measure 1 possibilities for this one. There's a fiber of measure 1 possibilities to this one. Let them vary independently. I mean, they have to vary independently, and this tells you exactly the measure over those V's that give this restriction to K. So you understand completely what happens there. So this is easy. I mean, there are a lot of other details to give, but let's say that this is easy. Okay, say that another possibility, okay, so from now on, it is trivial on K, but maybe it's non-trivial on L. Well, in that case, again, by just stability arguments okay, of the local theory, necessarily it has to be trivial on M. And it also has to be, it's basically like this. So you just take the canonical extension of evaluation from L to M, from L to LM, in a way that is trivial on M. There's a freest one, and you just take that one. Similarly, other way around, can be V restricted to M is non-zero, V restricted to L is 0. Okay, so that just same case on the other side. And finally, there is the case where both on L and on M, V is 0. But that does not mean that V is 0 on LM. Because what does it mean? It tells you that then that L embeds in the residue field, that M embeds in the residue field. So, okay, you can say that L tensor M goes into the residue field. But here they are completely algebraically completely free over K, and here they have some new algebraic relations. At least one, because otherwise the valuation would be even trivial on LM, and I don't count the trivial valuation, I don't care about it. Okay, so plus some new algebraic relations. And the whole problem in describing this free amalgam, LM, as a GVF is to describe those valuations. Okay. So the theorem the result I want to talk about is that in case 4, you can only have one new algebraic relation. Okay, so maybe at the end, if I have time. Okay, so as Udi said during his talk, in case you have some additional triviality assumptions, so for example, if either L or M is a purely transcendental extension, so there is no Albanese and whatever, and then this is enough to give a complete description directly of LM. So maybe I'll do that at the end just to give an idea. And otherwise, there is even more machinery you require. But if you don't have this, then there is basically no way to get a unique free amalgam. Actually, you would have gotten IP. Okay, now it's a theorem. So, but at the time it was quite worrying. Sorry. At the time, it was quite worrying that we couldn't do that. And so how would one prove such a result? Okay, so first of all, let me restate it in an equivalent fashion. So actually, for this one, I'm completely free in assuming that L and M are purely transcendental extensions because it's all about, algebraicity is not going to play, potent is algebraic relations between N and M. So we may assume that, okay, so say L is a purely transcendental extension, M is a purely transcendental extension. Okay, and we assume that X is independent from Y over K. I'm just repeating my hypothesis. And now what do I mean? So it's the finitely generated extensions, of course. So now, and assume that I have two polynomials, F and G, in K, X, Y, and so distinct algebraic relations, so say irreducible distinct.
Now K is anything. What's K?
K is a base GVF. Is it existentially closed with GVF? I'm now discussing independence over a fixed existentially closed GVF. Okay, we don't know how to characterize, or not entirely, but they exist because the class is inductive. So they exist, and this is the right criterion. I mean, being able to describe such amalgams completely is a way of showing that you have quantified free stability. Okay, so okay, let's say this, and you want to assume that if I have V is such that, okay, in the residue field, so first of all, V restricted to L and V restricted to M are trivial, but in the residue field, it kills both F of XY and G of XY. Well, then that cannot happen, so that means that the measure of V is equal to 0. So how would I prove such a thing? Let's try together to prove this. So assume not. Well, then first of all, just because of this independence, I can amalgamate many copies of this situation. So I can construct K with lots of xi's and with lots of yj's, such that each kxi yj is a copy of this situation. So maybe put all the xi's here, and maybe put all the yj's here, and then for each I and each j, I'm going to have a valuation vij, such that its measure is the measure of v, so measure of vij is greater than 0, vij of fxi yj is greater than 0, and vij of g xi yj is greater than 0, and it's trivial on, okay, I'm omitting some of that, but in any case, this happens for each ij, and it's actually, and these values are constant, they don't depend on I and j. Okay, fine, I can do that. So what? Okay, let's assume we knew one extra thing. Okay, so I'm going to add an assumption. So that's how we would hope to prove this. I'm going to slightly cheat, but I mean, all the right ideas are in what I say. So assume that you have a sequence of polynomials. Let's index them by d. Yd, I mean, okay, let's just, it's not important. Okay, so they are polynomials in xi, yj, say for I less than something, and for j less than maybe something else. It doesn't really matter. I mean, you can also make them equal. It's just, okay, forget. Let's take this one. Such that, first of all, PD vanishes on the zero set, on the common zeros. Of fxi yj and gxi yj. So you have now a square indexing a family of codimension 2 varieties, and I assume that PD vanishes on the union of all these codimension 2 varieties. And 2, well, I mean, you can always do this, of course. Okay, but so you want to put some constraints. So let's say, I mean, it's good enough, at least in the purely non-Archimedean case, that we can do this with the degree of PD not being too big. So I'm going to have mn times md times nd zeros, and let's assume that the degree grows strictly slower than this. Okay, let's just assume this. Well, in that case, what do I do? Well, then, okay, let's take ZD is going to be, just take PD applied to all the xi's and all the yj's for the appropriate I less than ndj. Okay, so this belongs to, okay, so this belongs to this GVF, to this big ambient GVF. And now, how many, let's see where ZD has positive valuation. Well, it's going to have positive, I mean, at least all these Vij's are going to have positive valuation at ZD. So for all ij, Vij ZD is going to be greater than 0 in a manner that does not depend on I and j or d or anything, and therefore I'm going to get roughly something that looks like md times nd zeros, at least. Okay, by zeros I mean places where the valuation is big. And so, okay, well, how about small valuation? Well, I mean, you can control it. Okay, so I'm slightly ignoring the fact that there's also the valuation of the coefficient. You can handle that. I'm allowed to. I mean, I'm cheating, but it's legitimate cheat. But you are going to get poles from substituting the xi's. I mean, basically, you can put all the coefficients in the parameters. That's what I'm saying. Okay, so you get poles from the parameters. You get poles from the xi's and the yj's. How many poles? Well, at most a degree. Poles, so bounded by the degree, up to constant multipole, and that's little o of md and d. Okay, so you get that you have strictly more zeros than poles, so the integral of v of zd d mu is going to be strictly greater than 0 as soon as d is large enough. Okay, and that cannot happen. Okay, so that's the proof. And we are using the, okay, this is how we use the sum formula here. Okay, so that was a strategy, and maybe if some people remember me walking around the IHP, asking people, do you know a result like this? Do you know a result like this? A long time ago, it was in 18. And, okay. And then we thought about it some more. And I still expect somebody to tell me, yes, this is known, but, okay. We finally managed to prove this relatively, okay, maybe roughly a year ago. And okay, we still, okay, there's some improvements to be done for the Archimedean cases, because then you also need to consider the size of the coefficients in Z, but okay, that can also be handled. Anyway, so the technical lemma I was referring to in my abstract was this result. Okay. So how would you prove this? I mean, it looks, okay, I mean, obviously, if it were not codimension 2, this would be false. If we were not requiring the degree to be small, it would be too easy. Why is this true? I want to draw something. So, at some point, relatively early on, Udi spoke with Karima Di Prasito, who suggested the following solution. Well, when f is just x1 minus y1 and g is x2 minus y2. This is the minimal, this is the simplest possible situation, because you need dimension 2, so you need something, I mean, you need both to have at least dimension 2, or else this trivializes completely. And this is the basic, this is the simplest situation. And what he suggested was do the following. Let's do a nice, let me do a matrix. Okay, so let's fix D. And now you're going to see why I call it D, because it's going to be a degree. So let's put on, okay, let's cut this matrix in half. I haven't decided what its size yet, but okay, you'll see in a second. And here, if I have I here, then I'm going to take all the monomials in, say, y I1, yi2, so namely, this is just yi, of degree at most d. Okay, so you can count, and you're going to be roughly, I mean, it's exactly 2 choose d. The important thing, it's roughly d square. I mean, up to a constant, it grows at the same rate as d square. And here the same thing, but with, sorry, this is going to yj. Y's are indexed by j today, sorry. And here it's going to be the same thing, but with xi. And here I'm just doing half and half. And I'm going to take the determinant of that, and this is going to be a polynomial, and that's going to be my PD. And now if you think about this for a second, it satisfies all the requirements. First of all, if I have a common zero of these two polynomials in any pair ij, that means that the point xi and the point yj are equal, so the two corresponding rows are equal. Okay, so the determinant is 0. So that's easy. And now let's calculate the degrees. Well, I have, say, d square, so the degree, degree, I have d square many rows, each row of degree d, so it's d square times d. And the number of zeros I get is, well, this one is d square over 2, so that's d square, and this one also, so it's d square times d square. I get strictly more zeros than the degree as d goes to infinity. That's what I wanted. Let me send it up because it's going to be, okay. So this is very nice, and when we got this message, I was like, oh, this is so easy. I mean, kind of humiliating because it's really easy. But I was happy, maybe Udi was also, I was happy because you just take this and you generalize to the general case, and you got your theorem, right? No. Okay, so then it took us a few more years to... Okay, and the problem, at least from my point of view, and given the proof that I know now, is that everything so far is extremely symmetric. I mean, even there when I said the U independent, I could have taken a symmetric, everything can be made completely symmetric up to this point. And here, the y's and the x's are treated in a completely symmetric fashion, and that's a horrible red herring. I mean, it misleads you. The situation is, I mean, the only solution I know is to break this symmetry, and the problem there is that somehow in the plane, a variety at a point, you don't see difference between different kinds of objects. They kind of coincide, and you're going to see soon that that's exactly what you don't, what cannot happen. And x's and y's need to be treated in a completely different fashion. Okay, so yes. Okay. Okay, so let's look at the general case now. What am I going to raise? I'm going to raise that thing. Oh. So let's break the symmetry. And so let's consider the y's as parameters for a variety in the x's. Okay, so general argument. So I mean, I can still say it's the variety defined by f and g, but really it's more convenient to just, okay, say variety. So say U is a subvariety. So I at some point I just get, it's easier for me to think in projective than in affine space. It doesn't change a lot. So it's a codimension 2 variety. Defined over k y. Okay. I can even assume that the definition uses y homogeneously. It doesn't matter much. Okay, so, but I also need to assume some technical assumption. I mean, this is my M, right? And I want to say that if I take a generic point of this variety, then I get my L. So I want to say that if I have x in U is generic over coefficients in ky, then it's just generic in Pn over k. So that tells you that basically k to which you add x. Okay, so maybe I want to say it's a projective point, right? So maybe I want to take the class of an x should be the homogeneous coefficient because I'm actually going to use coefficient. Okay, let's say it like this. Then it is generic over k. So k adjoined this thing is a transcendental, a purely transcendental extension. Okay. Okay, now let's build. Okay, so let's call this one. This depends on y. Okay, so let's even say that it depends on y0 because I'm going to take other y's. Okay, so now let's build a matrix. So I'm going to start doing exactly the same thing. I'm going to cut it roughly in two. Okay, so here I'm going to put just monomials in the x's. That's easy. What am I going to put here? Okay, so if here I put monomials in x's, so that's something that represent points in U. So here also I need to put monomials in something that represents point in U. I just don't have, I don't have any other way to make things match. So say I have a point z in Uy. Again. Okay, so I'm going to put monomials. So here now we are doing homogeneous stuff. So it's going to be, so monomials of degree d in Z. Okay, fine. Now take another point. Okay, so let's call this Z0. Okay, now take another point, Z1 in Uy. And do the same thing. So this is Z0, and now do the same thing with Z1. And go on until you can no longer do this because you get the next one, you get whatever point you choose is going to give you a linear dependence. And then you stop. Okay, so you have some block here, maximal, such that you don't get linear dependence. Well, what do you do now? I mean, actually, it's going to be a very small block, and I need some more. Well, I choose another y. So actually, I'm going to call this y0. y0 equals y, whatever. Okay, so this is at 0, 0. This is at 0, 1. And now I take z 1, 0 in U, y1, y1 algebraically independent over K from y0, so just a completely independent copy of my variety, and I do the same until I get, if I do one more, I get linear dependence, and then I stop, and I do another one, and then another block, and another block, and another block, until I get roughly to halfway, and then I stop. Well, and here I put monomials of degree equal d in xi. And I take the determinant of this, and I call this PD. Well, I mean, how many guys do you have here? Here you have, this is, so in this direction you agree that the length is n choose d plus n? Well, so now you know, you do roughly half of this, you fill with those guys, and the rest you fill with, and then it's square. You control, you have huge, here you have complete freedom. You just add more xi's and more xi's until you have exactly a square matrix, and then you take its determinant and go home. No, this is not good. Okay, so the way it looks, it's a polynomial. I mean, it's a polynomial over some, I mean, really depends on where I took all these points, right? So let's, for the time being, for just a short while, not state where I take this point, in which field. So I have a very large field called K bar. I don't know, just huge field. I'm out of letters, so I reuse K, but this is a very large field in which I can choose all these points. And then this belongs to xi, I less than, okay, call this nd. Okay, so let's first just do the easy calculations about the x's. Forget about the y's for a second. Now let's do the x's. So, okay, so how many zeros do I get? Well, each time I stopped once any additional point would give me a linear dependence. That means that if any of the xi's is a point in any of the uyj's, I get 0. Okay, so if any of the xi's belongs to u of any of the yj's, then, okay, and here, here let's say that I have md blocks. Well, then PD of, well, right now the yj's are kind of hard-coded into k. We're going to get rid of that later, but for the time being, let's just accept this of the xi's is equal to 0 because you get a linear dependence. So that gives you md times nd zeros. What's the size of, let's try to estimate md, let's try to estimate nd. So nd looks roughly, it's half the size. So it's roughly that thing, so it's roughly d to the n. What about md? So the size of each block is by the, I guess Hilbert-Samuel theorem. The size of each block is at most d to the n minus 2. Again, times constant. Okay, so each block, so each block is less than d to the n minus 2. So I get md is at least d squared because it's d to the n divided by d to the n minus 2. Okay, so I get a total of d to the n plus 2 zeros. What about the degree in x? Well, each xi has degree d, comes in degree d, and I have this d to the power n such guys. So it's d times d to the n. So that's d to the n plus 1. And that's good. That's strictly smaller. That's strictly smaller than d to the n plus 2. Okay. So I covered the zeros. I covered the degree in x. I want to cover the degree in y, but why is it even a polynomial in y? Okay, so as I said, I was a bit fuzzy early on about where I take these points. So I don't change, I mean, up to a constant coefficient, I can replace these lines by any, okay, okay. Up to a multiple. Okay, we may re-choose. The lines, the first lines, the top lines, just to give any basis to the generated space. It's linearly independent. They span a vector space. We can choose any other basis, and we are just going to change the determinant by some factor. So, but the point is that this vector space is defined, well, basically defined over k and the yi's. So this linear span is defined over just the field k with y0 to y, okay, md minus 1. So I can re-choose it, so we may assume that PD is simply is a polynomial over that field. And actually, well, I mean, the y's, there are transcendence bases, and they're algebraically independent from one another. So there isn't really much difference between these y's and formal indeterminates. I can just rewrite them as formal indeterminates. And then, again, up to multiplying by something in this field, I can actually replace this with just k of xi, yj, I less than nd, j less than md. And I can even do it so that it has no factor that does not mention xi. In fact, it's going to be it's going to be irreducible. But let's just say no factor in k with only the yj's. Okay, so I can actually make it a polynomial in xi and yj. The argument, I just go back to this argument, if xi belongs to uij, to uyj, then the same argument shows that this polynomial has to vanish, because you are going to get a point here that is in the linear span of those guys. So the only thing that's left to check is the degree in y. Okay, now I need to think strategically. No, wow, okay. And now I'm confused which. Okay. actually, there is a neat trick. I mean, okay, you know, when all you have is a hammer, everything's a nail. And since I don't understand anything about algebraic, I mean, basically the only way I can understand algebraic geometry is through, well, such things, and then Chow forms, and okay, and the big sister resultants, but here Chow forms are going to be enough. So basically, now I'm not going to go into the, okay, basically what Chow forms allow me to do is, so the Chow form of uy allows me to construct algebraically something that takes a family of n-2 linear forms and sends it to basically the intersection set, to, let's write it like this, a product for I less than D, D being the degree of the embedding of U, and okay, basically, okay, let's write it like this. Let's write it with D, with Z. So, so namely, product for over all I, oh, sorry, that's T less than D, sorry. So it's basically a product over all T of sum of X, so I use X star because these are not really, they are not the X's, they are in some sense dual indeterminates to the X's. So, okay, I just, my personal habit, so it's sum of X S Z T S. Well, such that the set of all ZTs is exactly the intersection set of UY with V of lambda. Okay, and this thing depends. So this is a polynomial. It can be split over the algebraic closure, and it depends polynomially on lambda and on the definition of U. So in particular, on lambda and on Y. So now I'm going to take lambda completely independent. So it's completely generic. Actually, I'm going to take several of those. In fact, I'm going to take in fact, what I'm going to do is, for each of those lines, I'm going to take a totally generic lambda. So again, you might as well think of it as an indeterminate family of linear forms. So, okay, so I have this matrix, and I'm doing something. So here it's still the same. It's xi's in the ith line, same thing. And here I'm going to look at, I'm going to take z whatever. I'm going to take it to be, in each line, I'm going to take u, I, y, j. So at this line, say I was at the level of u, y, j. So I'm going to take u, y, j intersection. Say this is the S line. So v of lambda s. And this is going to give me a family of generic points of u, y, j, and I'm just going to put each and every one of them here, and so I have d choices, so I have d choices here, and 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 I'm going to take for each possible choice of 1 point here, 1 point here, 1 point here, 1 point here, I'm going to build the matrix, take the determinant, and the point is that this just depends, again, polynomially on all the data. So on the y's and on the lambdas. So you just take the product over all possible choices of points among the D of each line. Of each line. And so I get a very, very nasty polynomial. And the point is that this polynomial is actually equal. You can show that it actually is equal to PD, okay, with the x's and with the y's, okay, to some power, to which power? Exactly to the power d to the power m, md, well, d to the power md times something that only depends on lambda, another polynomial that only depends on lambda and on y. And now you can estimate, this is something you construct quite explicitly, you can estimate its degree in y, so you get an estimate on the degree of y here. Well, the degree of y here is going to be smaller, and that's how you get a bound on the degree in y. So for each y you get, roughly, so for each yj you get basically, okay, it's big O of d to the power n minus 2, basically because you get, okay, constant times, well, n minus 2 lines. So, okay, I mean, I'm rushing my way here, but roughly this. And there are already, no, sorry, n minus 2, no, it's n minus, no, sorry, n minus 1, because there are n minus 2 lines, but there is also the degree d that comes in. So n minus 1, and therefore the total degree in all y's is going to be, okay, large O of d minus n minus, of d to the power n plus 1, and that is little o of d to the power n plus 2, and we are good. And, okay, maybe there are other ways of doing the exact same calculation, I don't know. I like this one basically because that's the one I understand. Okay. How much time do I have? Okay, so let me just now say briefly, maybe complete what, as I said, what Udi said about things being really easy in the trivial case. Okay. Okay, so now, particularly easy case. Okay, so this I proved my lemma, and therefore I proved my theorem. Now I'm going back to describe LM when L is independent from M over K. And again, maybe use finite satisfaction. It doesn't matter, just whatever. Okay, so, but in the easy case, where, say, M is a purely transcendental. I want X's, let's call it L. Doesn't matter. Is purely transcendental. So again, in order to prove the various results I proved so far, I could easily reduce to the case where both L and M are purely transcendental, but now I want to actually describe the GVF structure, and then, I mean, knowing the GVF structure on transcendence basis does not give me enough information. So this is not a legitimate assumption, it's just an example. So now, so LM is MX. Well, so what do we have? I mean, so I know I already took care did I erase the 4 cases? Oh, I did erase the 4 cases. Doesn't matter. So I want to describe. So I have omega Lm. I already know that Lm. Well, I already described the field, the pure field Lm. I want to describe this guy with a measure. Okay, so assume I have evaluation here, and we already said that we know exactly how to describe V is okay. Already we know. Okay, so it's completely known. The measure on V's that are either non-trivial on K, or at least basically non-trivial on either L or M, or on K and therefore on both. Okay, so this is okay. Maybe this is known. Okay, so we left to describe the second case, which is V trivial on L and M. Okay, and now we know that it is on the residue field, V is so the residue field just adds a unique algebraic relation between L and M, and given the form of this, it basically means that so the one algebraic relation just means that V is the p-adic valuation for some P in M in Mx. Irreducible and not in Kx, because that's covered by previous cases. And if it's, on Kx, it's just something that happens on L. Okay? So just introduces one algebraic relation, P. Okay, so what I'm going to do is just look at the sum formula for P. So I know that 0 equals the integral of V of P d mu. Okay, that's the sum of the integral over I and the integral over 2, over 1 and over 2. And this thing is just the measure of Vp. Because all the other guys here are going to be Vq for another polynomial that's not a multiple of P. Okay, so just the measure of Vp. Okay, so the conclusion is that the measure of Vp has to be equal to the opposite of the integral over the first case of V P d mu. And I just gave you, well, okay, modulo the fact that you accept that I can do the first part relatively easily, I just gave you a complete description of this amalgam. So again, that doesn't prove stability because this is not the general case that we need to treat, but give some idea of, it's an easy hands-on example of how this only one relation can be used to give such a description. Thank you.
Okay, thank you very much. Are there any questions? Oh, you did have a shout.
Yeah, I was a bit confused. So is the only one relation thing, is that saying that you have all of the valuations of the fourth type that are relevant in this product, for each one of them, there's only one algebraic relation?
Yeah,
Or
so
saying that there's only one valuation?
no. There are many such valuations, and for each one, you get a different residue field, a different map sending the two big fields into the residue field. possibly introducing new relations, and in each case, it introduces exactly one new relation. Yes?
In the sum there, how did the second half of the sum turn into the only one? You have a bunch of primes, but then
Because I'm looking here at the valuation, so this is, I'm integrating V of P. So the only V, so on the second kind, the only V that can be non-zero on V of P is VP.
Any other questions, please? No. If not, then let's thank